Hello, everyone. I'm Dr. Tina Burns, and this is Lecture 6A, or the first lecture in week 6 of this course. Um, so let's kind of go over the roadmap of what we'll be discussing today. We're continuing with our discussion of cache. So we're going to review some of the cache terms, then we'll go over some bit calculations. We're going to look at some data flow examples, and then we'll talk about locality. That's how we end the class. So when we think about terms, as we're evaluating cache, one of the things you want to understand, especially for your final project, is what is a set? A set is defined as a cache line of multiple blocks, right? So if I have a line of data, then what will happen is I will have multiple blocks within um, that cache line, right? A block or a line is just a cache storage unit. So it's just referring to how I want to look at the data inside there. It's just a block of information that details my cache storage unit as a whole. Your tag, that we talked a little bit about this in class before, it's just gonna tell you what's the location in the main memory this refers to. So when we look at our cache identifier, our tag is everything left over after we finish getting the set location and the offset and all that. Then what we're left with is the tag, which will have a direct reference back to the actual address in memory, main memory. Now, when we look at mapping variables, right, as we do some of our problems, what we'll see is, of course, we're going to use shorter terms or variables to represent these items. So we'll have something that's called S that'll typically be for your cache set. N is typically going to be for the number of lines or blocks in a set. A word is referred to as a word is the same thing as a byte. So a word is 8 bits or 1 byte. They're all synonymous. Word, byte, it's synonymous. It's the same thing. So if you see that in some of your examples, don't get confused. Just know that a word is a byte. So one word is 8 bits of information. When we talk about offset, an offset refers to the number of bits used to store the cache lines or blocks. So keep in mind that when I represent a memory address in the cache, I need to have some bits that are specifically allocated towards telling you where it is in the cache. So this offset bit is what's offset bits are the number of bits that are used to tell you how many, I'm sorry, are used to tell you where your element is being stored in the cache memory. V is our validation bit. The validation bit just tells you whether or not this cache reference or address is actually valid. Does it make sense? So let's look at this layout and kind of a example of this pictorially. Let's say you have something, you get an example where it says you have 2 lines and your total number of blocks is 8, right? And then it also says, hey, what do I need for my sets? Because I said previously that your sets is going to be defined by the to your all the blocks you needed, how many lines are in that particular block. If you have both those elements, you can determine how many sets are in your cache. So here's kind of what it looks like pictorially. If I had, let's go ahead and bring over our annotation toolbar. So I have this, right? I have my validation bit, my tag, and then my word. It's the data or the information. And this is telling me the memory, location, or address, and all that information in there, right? If I were to break this down and say, what is each one of these? Each row here represents a set. Each row, this is a cache set. All right. So that means this is set 1, 2, 3, 4. Every row for this, the way that is represented here is going to be a cache set. Now, when I talk about the number of blocks, this is one block of data. So there's a total number of 2 blocks of data, right? In each cache set. Notice how it has that. There's 2 blocks or 2 lines in one set. So this is a two-way cache, right? Because I have 1, 2 lines or 1, 2 blocks of data in one cache. So this is known as a two-way cache. Here is the first set, and within that set, these are my two lines or two blocks, however you want to refer to it. Here's one set. Here's my two items that are in that set, and I go all the way down the line with a total of 8 blocks that are in there. So each set has two lines in it, and that's how we get this example in terms of how this looks, right? So again, this is a two-way cache, right? With 4 sets. So that's 4 sets of information. It's two ways because it includes two lines here. All right, so let's clear all that. All right, let's look at an example here, right? Or let's go and talk about the total number of memory. Remember this in terms of what we've been using in this class as a representation of how we would do our bit calculations. We have your total number of bits, total number of, sorry, your total memory is basically going to be given by the total amount of bits that you have for your main memory. Offset is going to be help us to index the cache line or block. Um, and then index is going to tell us the number of cache sets. So is OB is a good way to look at it. Your offset is going to tell you the number of blocks or the number of bytes in line, OB, how many bytes are in a line. Your your index, IS, is going to tell you number of cache sets, so ICS. Index is for cache sets, right? Your offset is going to be bytes per line. And then your total number of memory, of course, is going to be your total number of memory. Or your tag, that's the easiest one to do because that's typically is what is left over after you get your offset and your index. You can take that and subtract that from your number of total bits for the memory, and you can get your tag. Um, and that's going to index your memory location or tell you where you can find that in main memory. All right, now let's look at some examples. All right, so let's say we have a set associative cache with 8 sets. All right, so keep that in mind when it tells you this information. It has 8 sets of information, 8 sets total, and each block has 16 bytes or is 16 bytes inside if the cache is an 8-way cache. Huh. And the addresses are 32 bits. Determine the bits for the tag, index, and offset. So I looked at that because I'm like, it's interesting that we would have an 8-way cache and 8 sets total. For me, that's telling me that it's going to be one set per each way, which is kind of like, it's not going to be an exact direct map, but you're not going to have multiple lines, I'm guessing, in one set. But let's go ahead and go through the example. Now that I've let's go ahead and go through the example. So the first thing we can tell, if I know, I already said is, right? My cache, the is or the index is going to be determined by the number of cache sets that I have. And I already know also that my the offset is determined by how many elements or how many bytes are in my how many bytes total are in my in each block. So the offset is an easy one to do, and the index is a relatively easy one to do, right? The offset, I said, hey, I have 16 bytes total within here. If I know I have 16 bytes, I know that my offsets or the number of bits I need to represent each block, the word in each block, I just can take the log 2 of that, and that's where I get 4. For my index, I'm sorry, yeah, for my index, which is going to give you the number of cache sets, I can say log 2 of 8, which should give us a value of 3. And that will be how we determine what our index is, right? Then what we're left with is what can we do to find out or determine our tag? Well, I'm going to actually write this out, right? All right, I already know that My address is 32 bits. That's my total memory. If I subtract 4 for my offset and I subtract 3 for the index, I end up with 32 minus 7 or 25. So 25 bits then would be associated with my cache. 25, that is not right. Let me just go ahead and delete that. My index, we've already determined is 4, right? It means I need 4 bits to represent how many bytes are in each line. And then my offset, how many bits do I need to represent my number of sets? It's going to be 3. And that should be the final answer here. So let's go ahead and clear all this. And there it is. So that's the final calculation for that. Let's look at another example. Why did I give the same example here? I gave the exact same example. So let's look at, okay, let's look at another example. Apparently I put the same example twice. That's fine. All right. So, actually, let me just go ahead and get rid of this really briefly since we don't, or did I just go back to that? Oh, maybe I just went over it multiple times. All right. Let's just start where we are. All right. So, we have the main memory that is 256 megabytes. So I can already automatically tell you that the first thing we're going to need to do is, or at least at some point, we're going to need to determine how many, we're going to need to determine how many bits is my main memory, right? And then we also need to do some conversions here to get this really in the total number of bits, right? So we had that example that we went over in class before that gave us kind of this outline of what we needed for byte representation. As you go there, I'm pulling this up. So I know my total memory bits. I'm just doing this for my own reference. You'll see this later in the example. Total number of bits for memory is going to be 256 megabytes, right? Which is going to be 256, I think is 2 to the, we'll look that up later. Mega is going to be times 2 to the, now kilo is going to uh easily be represented as 10. Mega is going to be represented for your 20 here. So then I just add this to whatever that item is going to be. All right, so as we look at this, we have 256 megabytes for our main memory. I know that 2 to the 5th is 32. So I'm just going to go down here, 2, 4, 8, 16, 32, 64, 128 to 56. All right, 1, 2, 3, 4, 5, 6, 7, 8. So I'm getting 2 to the 8 here for my calculation for that, which means the total number of bits I need for my total memory is going to be 28. All right, let me just check this with my solution set. Yes, 256. I ended up getting the same thing. Megabytes is going to be 2 to the 20. The other calculation is going to be 2 to the 8 for the 256, and that's how I get 28 bits. The next thing I can calculate is my index. Now, your index is relatively simple, right? No, actually not my index. Let's go back here and calculate the offset. The offset is a total number of bytes uh, per line, per cache line. So if I tell you that, or block, for cache block, or blocker line, right? So if I tell you there's 128 bytes per line, then I can calculate what I need to get to represent this by just taking the log 2 of this. So log, ooh, I didn't want the answer. Ah, fine, we'll do it that way. So the log 2 of 128 will give us the offset. The offset again is total number of bytes for each block, each cache block. All right, so now I have my main memory size. I also have my offset, and I can continue this further and then determine what my index is. Now your index, right, is ISC. Your index is going to tell you the number of bits you need to represent a cache set, right? How many bits I need to represent my cache set. The thing about this is there's two items of information you have here. It's saying that I have a two-way cache, right? But I'm also given that my cache size is one megabyte, right? So I want to include that information in my details a little bit here. So we're going to move to this next line. The first thing I want to look at is how many lines are going to be in my set total, right? I'm not given the number of lines here, so I need to calculate that. Now, keep in mind, as I was saying before, right, if we go back to our main definition, and yes, I'm going back to that just so that we have a really clear understanding of this. When I look at we're looking at the how to index the cache sets. If I look at that as an example, indexing the cache set is going to end up being kind of my total number of blocks divided by my total number of lines. That will tell me the total number of sets I have entirely in my cache. So I need the total number of blocks and the total number of lines in there. So that's why this gets into a little bit more of a interesting calculation when we run it here, right? With that one. All right, I have my offset, I have my memory. Now we're looking at what do we need to do for this, the index. How many sets are in there total? That's pretty much the question is how many cache sets do I have and how many bits do I need to represent that? All right, so the first thing I want to look at is my block size and the cache size. This will give me my number of lines, right? If I know how many blocks I have and I know the size of my cache, automatically using these calculations, I can get the number of lines, right? One line is a set of multiple, like it's a unit, it's a set of blocks that you're using within the cache. So this is 1 megabyte, which is going to be 2 to the 20. If I divide that by my block size, then I can get my line number, the number of bits represented for my lines. And that's going to be 2 to the 13. Now, I'm going to take that and say, if this is a two-way cache, it's a two-way set associative cache, then that means how many each way or each item, right, for each cache set has 2 lines in it. It's two-way, so each cache set has 2 lines in it. All right, now that I know it has 2 lines, how many bits do I need to represent this? So I take my total number of lines that I have, and then I basically divide that by my set bits, and that's how I get a value of 12. So there's a total of 12 bits that are needed to represent all of the sets that are in this particular cache. All right, now moving on, my index bit then becomes 12. And of course, after that, the only thing that we have left is calculating the tag bit, which is going to be 28 minus 12 minus 7. 12 and 7 gives a value of 19. So my number of bits needed to represent the tag, or what I have left for that, is 9 bits. So hopefully that makes sense. If not, go over the lecture a few times so that it becomes a little bit clearer to you. But the main thing that I wanted to demonstrate here is that if you're given a problem where you have something that doesn't explicitly give you the lines, then you have to calculate the number of lines in order to get the total number of sets. So just keep that in mind. All right. I've talked enough here about this. I beat it all over the head. So hopefully you guys have a little bit of a better understanding here. Um, Now let's talk about another item. This is for our bit calculations. What happens when we have, we talked about in the last class an LRU replacement policy as well, meaning if I have a set of instructions, these are all represented as instructions, and I want to determine what's going to be this final value in my cache or how that looks at what is the data flow and what are the items that are there. So let's say we have this example, given a set associative caches with 4 sets with an LRU, that means least recently used replacement policy, identify the elements that are replaced by the last line. Well, the first thing we need to do is to identify the elements that go into each portion. The first 4 lines are relatively easy. They are all independent variables, and each time it changes, so that's super easy to do, right? This is going to be A is equal to 2, B is equal to 3, C is equal to 4, and D is equal to 0. That's relatively easy. Every line is going to a different place in the cache. That's super easy. Now, as we continue though, what happens next? Well, as we're dealing with this replacement policy, we have these as the first 4 instructions. The next 4 is what we want to kind of look at. So then the next floor, what happens is I have a replacement policy that says I'm going to replace something, but I'm only going to replace if I found that variable or item in my cache already, then what I do is I update that. So A is equal to 0 now becomes A is equal to, I'm sorry, A is equal to 2 becomes A is equal to 0, right? That makes sense. For D is equal to 1, I'm changing this to 1, right? D is equal to 2. Okay, now this no longer 1, this becomes 2. Then I have B is equal to 5. Boom, that becomes 5. Then I said C is equal to 1. Boom, that becomes 1. Then I have A is equal to 3. Boom, that becomes 3. So from these 6 instructions, my final value is A is equal to 3, B is equal to 5, C is equal to 1, and D is equal to 2. So my next 6 instructions then looks like this. Oh, wait, did I do that right? Yeah, my next set of instructions then looks like this, where A is equal to 3, B is equal to 5, C is equal to 1, that is the last known item, D is equal to 0. Then the question becomes, what happens when I get these 2 new commands? These 2 values are different variables. That means somebody is getting booted out. Somebody's getting evicted from here. So who's getting evicted is the question. So in this instance, that basically means that this is based on what was least, what it's least recently used. That means what has not been accessed in a while. So if I were to determine, for example, where this first line is, I first need to look back at my previous instructions to see what was located. Let's look at all the variables we have, A, B, C, and D, right? So if I were to write those out, right, A, B, C, and D, there's multiple ways you can do this, right? And what you can do is you can look at it from the back lineup, or you can also write in what has been, and then we'll say, I'm going to put I and J down here as my next numbers. If I said A, B, and C, A was my first element that was accessed, B was my second, C was my third, this was my fourth for D. Then I accessed A again, so I had and you guys probably, you can use a different method if it works better for you. This is just for me, so I can keep track of this. There are easier ways to do this as well, but this is the way I've selected it. Choose whatever method works for you. All right, now I'm at this point. where D is my fourth line, A is my fifth line, my fifth instruction, D is my sixth one, right? So I'm here, 1, 2, 3, 4, 5, 6. D is also my seventh instruction. B is my eighth instruction. C is my ninth instruction. A is my 10th instruction. So I'm at the 10 instructions. And now I come to this, which is instruction 11. All right, so based on this, I have no more space here. I have 11 instructions that were already executed. So let's just walk back and determine which of these items are going to be replaced. All right, so I know it's gonna be back a few. It's not going to be 10. It's not going to be 9 or 8. So it's going to be something in 7. And I see that the seventh instruction, actually, I'm sorry. What was the question is what item was least used? So if I just look at these values at all, I can look at here for my row and determine which of these variables has the smallest number, right? It's not A. A has the largest number, right? That means the one I just accessed recently. It's also not these. These have pretty large numbers. If I'm looking at the last item here, D appears to be the one with the last or the smallest number or the one that was least recently used. So then that means that I'm going to go ahead and boot out D and make this equal to I is equal to 0. All right, now I have this. This becomes line 11. Now I'm going now to J. All right, J, what am I going to replace here? Well, this number is pretty big, so I know I'm not going to replace that one. I just did that one. I'm also not going to replace this one. That's 10. I'm not going to replace this one. That's 9, right? So now I'm through 3 lines, right? Do I replace this one? No. Do I replace so no for I, no for A. I'm going to take that out. And then I have B and C that are left. Am I going to replace B? No, that looks like it has a pretty relatively, I'm sorry, C looks like it has a recently used one, so I'm not going to replace that one either. Either B is the one with number 8, so that means I haven't accessed this until my value for 8 was done previously, so that would be the next one I'm going to replace. That will be kicked out, and this becomes J is equal to 0. So that's how you kind of go through. You want to look at this least recently used means what element did I least use, and that's the one that's going to be replaced. So we see that D and B were both these items that were kind of just sitting in memory for a while. So what's been sitting in memory for a little bit, that's what's going to be booted out. Okay, now let's go ahead and clear all these guys. And you'll see this is our solution set. If this will allow me to do that, it's going to show you where we kind of replace those two sets 4 and 2, right? All right, now this was for LRU. What if we were using FIFO? All right, I now have the same question, but now I'm using this first in, first out strategy. That makes it a whole lot easier because what that means is the set that I used first, that's going to be the one that I'm replacing. That's going to be the element that is going to be replaced sooner. So if I look at how often these sets are going to be replaced, this one is replaced just like the number represents here, 1, 2, 3, 4. I'm always going to replace this element first. I is equal to 0. And this is going to be second. J is equal to 0. Those are always going to be, if my cache is full, these are always going to be the elements that are replaced. It just represents the data that's kind of within that cache. Now, it's really easy to do this. If you look at this in terms of, if you arrange these in order from 1 to 4, I already know automatically as soon as it's full, I know which element I'm replacing because I know the order in which this is going. Whereas LRU, you have to do a little bit more manipulation to determine which one was accessed previously. I'm going to go back to that LRU example because I want to show you guys maybe a little bit of an easier way to look at that. So let's say we're looking at these last two instructions. And instead of me looking at each variable, I can also look at this in terms of each set location, right? And I can see what was accessed first. It's relatively easy to see that, okay, I know I'm going to access this first. So I'm going to put one line there, one line there, one line there, one line there. All right, then what I do is I'm going to access A again, boom. I'm going to access D again, boom. I'm going to access D, A, D, D. I'm going to access D a third time, boom. Um, then I'm going to access B a second time, boom, right? And I already know how I'm accessing these, right? So this is the memory address I'm accessing. I'm going to access C. Now I'm down here. C is going to be my recent value for that one. And then I go back to A. So I've already seen kind of the ones that are most recently used most often or used least often. And if I look back from the top on up, I can see which one I'm not going to replace in terms of instructions. I know I'm not going to do this one, right? This is the last one I did. I know I'm not going to do C. I did that right before. I know I'm not going to do B. I did that right before. So A, B, and C are out, which automatically tells me that this is the memory address I'm going to be replacing. So hopefully that made a little bit more sense. All right, guys, let's go on to our next item. Let's clear all this. Clear the whole drawings, and now we're going to go into locality. And that's gonna be where we end our class with. So what is locality? We're going to go through a little bit of understanding that in why it improves the cache performance as we look at our these concepts. So the first question is, what the heck is locality? Locality or locality reference is just how often you access the same memory access address. When is it accessed, and do you think the items surrounding it are also going to be accessed with the same frequency? And there's two things that we're going to talk about specifically today. If I'm given this example, right? If we look at this as just an array and the addresses are represented by hexadecimal numbers, uh, if I had something like this that was accessed over and over and over time, that will be something known as temporal locality. That means that I can reference this same memory location at multiple times in the program. So I have it here, I have it here, and I have it here. This is accessed several times in one particular time frame. That's known as temporal locality. Now, there's also something known as spatial locality. Spatial locality says, okay, I've accessed this address, and the next thing I'm going to access is this, this, and this. That means that the addresses that are close to each other are likely to be accessed next. So the locality reference says, okay, how can I save time? And I can do that by determining what I expect the next address to be, right? So if I'm expecting that I'm going to be getting this over and over and over, I may want to store this address so that I can easily access it in the cache rather than going to main memory for it. If I know I'm sort of going down to the line and I have this one, but I'm in an array, I'm probably going to access the next one and the following one. Then I have something known as spatial locality, and I may want to store the addresses next to the address of interest within my cache. All right, so let's talk a little bit about spatial locality. So spatial locality, keep in mind, this is this guy, space, right? How many times within a particular space, physical address, location, am I going to access this? So this is a representation of spatial locality, accessing the same elements that are near to each other, um, right after each other. So the question for spatial locality is this close to a frequently accessed item? Is this address near something we already access frequently? The second thing you want to remember is that spatial locality is based on proximity. So how close is it to the address that was already a accessed? Now, for your spatial locality outline is that it's going to, of course, get these locations that are near each other. And its benefits is that it's going to improve your cache hits by preloading adjacent data, right? So some people call this like prefetching. If I know my program is probably going to access um, these elements in the array, what I can do is when I get one, I can go ahead and prefetch these other items. If I know I have an array and I say, okay, array is at zero, x 800, why don't I go also and access 800, 801, 802? I prefetch that information, and then the next time I perform an instruction, if that's already in the cache, and it saves time for me missing the information. And of course, you're going to use this a lot, which makes sense. You're going to use these a lot when you have um, arrays and you're dealing with processing those arrays and you're dealing with things in data structures. So we would use them very often, right? Data structures, linked lists, binary search trees, you want to print out all the names in a class roster. You're doing that through some sort of linked list, right? You want to take the elements all in an array and you want to add 5 points to each of the student grades, right? So you want to update what their final score is. Then you know you're going to be accessing the next items in those array, so you can go ahead and just prefetch those in order to save time and to reduce your number of hits, reduce your number of misses. That's spatial locality. Here's an example of that, right? If I had this program here, right, and I was writing this out and I had just a very simple array here, you would initialize it and just put, for our purposes, we'll put a bunch of random numbers in there. Um, and then we want to look at what this spatial locality looks like. We have this guy, which means I'm going to access each of these array elements one after another. Very common in arrays. Every time I run this, I'm going to do these sequentially. So I'm going to go from one, I'm going to keep on going up and incrementing, and then just adding to that array. So I'm accessing the addresses one after another in terms of the instructions from my program. And that is what we would call spatial locality, or using that because I'm referring to uh, each element being at a different address, but I'm accessing that contiguously. I'm accessing that right after each other. And here's a prime example of kind of how that looks. I'll go here, 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 and then there. Now, if I looked at this in terms of a direct map example, let's consider we have this. Look at our addresses here on the left-hand side, and look how we're indexing these. We know we're going to have this as a block line, but I may also want to include this in my next block, and this in my following block, and so on and so on. When I do that, I have this as an index and I can pull out all of this information because I believe that I'm probably going to be accessing that in the next example. Now let's talk about temporal locality. Temporal locality, as it indicates, is based on time. So how many times over time, or how frequently do I access that item? Is this memory address accessed repeatedly? And of course, it's going to be based, as I said before, on your frequency. Now we'll see this if we're going to reuse data within a short amount of time. And this really helps us with prefetching. So if I've gotten this item multiple times, what I'm going to do is I'm just going to keep that in memory because I know that I'm going to access that again and again. Now, this is going to be really, really helpful when you're dealing with loops, right? For loops, while loops, because you might be doing the same thing over and over and over. Let's say I have something and I am doing a calculation where I'm going to always be updating this one variable. This would be really great because I know I'm going to access that over time, so I'm going to go ahead and keep that data. Here is an example for that as we look at how we're going to kind of access these information. Now, with the differences between these two, this top one is going to be the same. You're just doing a bunch of random variables. But if we look at this one, right, um, when we demonstrate this temporal locality, notice how I have this k is a variable, and I'm just going to run this loop 100 times. And what I'm doing is, rather than accessing different components of this 2D array, I'm accessing the same one um, over and over. So over time, I'm accessing these same particular variables, right? If we look back at the other example, I was accessing array elements that were right next to each other. But now I set this to 0. So that means I'm not accessing every adjacent row element or every adjacent row element. Rather, what I'm doing here is I am accessing certain elements repeatedly over and over within this loop. All right, so since I know I'm accessing this multiple times, which means I'm doing this from 0 to 100, so this is gonna repeat. I'm gonna go ahead and access, each of these component more than once. Then I want to store those in my memory address rather than it just being based on solely the location or how the proximity it is to the current address. All right, so that's what I have for today's lecture. Oh, I'm sorry. Let me finish this guy. So for this one, you're talking about how many times is this access over and over, right? If I keep on accessing this, for example, again and again, if I were to let's go ahead and put if I said I access this, then I access this, then I access this, and then I went back and I said again, again, okay, again, again. That's what's known as kind of this temporal locality because I'm accessing this multiple times within a certain time frame. So why do we care? Why do we do this? And what is its impact on our cache performance? I'm glad that you asked. Um, Here's what we get. We get an increased number of hit rates because we can prefetch data, which means if I suspect what I'm going to be accessing, I can go ahead and put that in my cache, and I don't have to worry about the cache misses. It's going to reduce your latencies in your data access because it's already within your cache, and then also it's going to help with your system performance overall. Now, keep in mind, I usually include my sources at the end of my slides. I do want to make a note of that because as you guys work on your project, please make sure you reference appropriately the sources. Even if, part of the sources are me, you can go ahead and say, Dr. Tina Burns, lecture 6A, blah, 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 cache memory, whatever. Just make sure you keep that in mind as you're doing your project, as you're doing your report referencing your sources and where you got the information from is important. It is vital. Even if for parts of the report, you generate, you have inquiries and different things that you request from like AI, just make sure that you reference that. Keep in mind as you do your project, as you do your report, you should be writing these independently, meaning do not just use AI to write it or to do your code. But if you can use different things as resources, all I'm saying is make sure that you note those resources in your sources section or your works cited page. All right, I think that I'm done babbling for now. Thank you guys for joining me. We'll be back for the next lecture in 6B. And 6B, I think we're done with cache for now. So 6B will be going on to the next topics, which I believe are loop rolling and unrolling. I got to check and look at what I put on the syllabus. But either way, if for your cache information, I would highly reference the slides here and also what we talked about last week. All right, guys, enjoy the rest of your day.